This nutshell looks at the analog to digital converter. I review what the ADC does. I look at circuit examples. I show the ATmega2560 ADC system. We look at the registers used by the ADC and how they operate. And I give coding examples for both single and multiple channel conversions. And if you find this nutshell useful, please like and subscribe. There are two types of signals. The analog signal, which can have any voltage between 0 and VCC, and is known as a continuous time variable signal because the signal is there continuously. Digital signals have only two voltage levels, 0 and VCC. And we look at when they are sampled on the ADC, they are sampled at a specific point in time. So they are not continuous. Instead, they are discrete time variable signals. So the microcontroller is a digital device that only uses digital values. If the input is an analog signal, then we must convert that signal into a binary number. This action is performed by the ADC, and the number that is converted is proportional to the input voltage level. The graph here shows both the analog signal and the digitized signal. We can see we have sampling points here, 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 and here. And we can go through the whole waveform looking at the sample points. The ADC is 3 bits, so therefore we have 8 voltage states. And we can see that we have errors between our reading of the analog input. For instance, we're reading here, we're saying the analog input is 011, but it's not quite. We can see the reading here is fairly accurate, but the reading here, once again, we're saying it's 110, but it's not quite, slightly above. So that error is called quantization error and is dependent on the resolution of the ADC. The resolution of an ADC is the number of steps the ADC can divide the input voltage range into. It's shown by this formula. Resolution is equal to the power of n, where n is the number of bits in the ADC. So if we look at examples, an 8-bit ADC will have 256 steps. The 10-bit ADC will have 1024 steps, and the ATmega2560 has a 10-bit ADC. A 12-bit ADC has a resolution of 4096 steps. The resolution relates to the voltage resolution, and the voltage resolution determines the smallest measurable voltage we can look at. So the formula for that is Vref over resolution. So if we have a 5 volt reference, then an 8-bit ADC will have a voltage resolution of 19.5 millivolts. A 10-bit ADC has a voltage resolution of 4.88 millivolts. A 16-bit ADC has a voltage resolution of 76.3 microvolts. So you can see we can be more accurate if we have a higher resolution ADC. As I described before, the quantization error is the difference between the actual analog input and the digital word that the ADC converts. The ADC compares the input voltage that you're converting to a reference voltage. The Mega2560 has 4 reference voltages, 2 internal, the analog power supply, and an external pin which can have the reference voltage applied. Now, if the ADC input voltage is greater than the reference voltage, you can use a voltage divider to reduce it. If the ADC input voltage is small compared to the reference voltage, then you can amplify it to allow the ADC to use its full input range. When you're calculating the ADC converted word, so we have the input voltage here, we multiply it by the resolution over the reference voltage, that will give you the value of the digital word that was converted. Similarly, we can work backwards. We can find the input voltage from the digital word by applying this formula here. So if we look at an example below, we have a 12-bit ADC, reference voltage of 3.3 volts. Therefore, the resolution is 4096. The voltage resolution is 806 microvolts. If we had a 3.0 volt input, the digital word would be 3723. That's it in binary. Or if we want to convert the word back to the input voltage, say we had 4032, then that would mean the input voltage was 3.2484 volts. Now when you're looking at the conversion speed, the ADC must convert fast enough to follow the change in the analog input. So therefore, if you have a high frequency signal, the ADC must have a fast conversion speed. This schematic shows 3 analog sensors connecting into the ADC system. We have the temperature sensor going into ADC2, we have a potentiometer going into ADC1, and we have a light sensor going into ADC0. And the power supply here is not strictly correct. The analog VCC should also be connected to the 3.3 volt system. The ADC inside the ATmega2560 has 16 analog input channels, and they are passed through a multiplexer to a single ADC converter. The channels are grouped into single and differential channel inputs. The single channel inputs, the ADC converts the voltage difference between the analog input and ground. With differential channel inputs, the ADC converts the voltage difference between two analog inputs. And some selected channels have gains of 10 and 200 selectable by software. The ADC has also 4 reference voltages. We have internally 1.1 and 2.56 voltages. We have a ref on the external pin, and we can look at the AVCC. We can see the internal architecture of the ADC here. At the heart of the ADC is a 10-bit converter with a VREF going in and analog V in. The converted output, which is 10 bits, is stored in ADCH and ADCL. The ADCSRA, some of its tasks are to power on the ADC and prescale the clock. The ADCSRB, part of its tasks are to select a trigger source and to be part of the multiplexer. The ADMUX has the multiplexer, so we actually have 4 multiplexers. We can multiplex the VREF. We can look at selecting one of the single channel ADC inputs with this multiplexer, or we can combine these multiplexers here for the differential channel inputs, which are going into the op-amp. The op-amp also has gain on some selected channels. There are 5 registers used by the ADC. The first 2 are the ADCH and ADCL registers. So the converted 10-bit number from the ADC is stored in the ADCH and ADCL registers, which are combined together to create a 16-bit register. So the ADCH contains the top 8 bits and ADCL contains the bottom 8 bits, and the converted numbers can be either right aligned or left aligned. For the full 10-bit resolution, you should right align the results and use the ADCW, which accesses both ADCH and ADCL, and that way we get the full 10-bit resolution. If you only require 8-bit resolution, then you should left align the results and just look at ADCH and ignore the 2 least significant bits in ADCL. The ADCSRA register is used to configure the ADC. Bit 7 is used to power the ADC on or off. Bit 6 has 2 functions. Writing a 1 to it starts the conversion. When the conversion is complete, the results are stored and the bit is cleared by hardware. If you're running in free running mode, you only need to set the conversion once, as it will automatically repeat. If you're using single conversion mode, then you need to set it for each individual conversion. We have the selection for the auto trigger. If you set this bit 5 to 0, then that's single conversion, where a single conversion is performed and the ADC stops. It needs to be started again for the next conversion. If you write a 1 to that bit, it enables the auto trigger mode, and the conversion is performed by the trigger event that's configured in the ADCSRB register. If you're reading multiple channels, use only single conversion and switch between channels. If you're reading a single channel, use the auto trigger. Automatically, by default, the trigger will be set to free running, where the conversion repeats automatically, so you can just have this free running. We have the interrupt flag register set by hardware, the interrupt enable, which we'll talk about later on, and then we have the clock prescaler. Effectively, you really should have this set to a 64 or 128 division ratio. The ADC control and status register B has bit 3, MUX 5, and this is used in combination with MUX 4 and 0 in the ADMUX register to switch the multiplexer to the desired input channel that will be fed into the analog converter. We also have bits 2 to 0, which are the ADC auto trigger source. They are used to select the trigger source that will start an analog conversion. By default, the trigger source is free running, where the conversion is repeatedly started after a conversion is finished. Use free running mode when performing single channel conversions. Looking at the ADMUX register, we have bits 7 and 6. They are used in this table here to select which reference voltage the ADC will use. Bit 5 is for the left adjust. If it's set to a 0, we right adjust, and we will use that for 10-bit resolution using both ADCH and ADCL. If it's a 1, we left adjust, and then we use ADCH with only 8-bit resolution. Bits 4 to bit 0 are the MUX 4 to MUX 0 bits, and if we go back to the ADCSRB, we can see bit 3 is the MUX 5 bit. These bits are used to select the input to the analog converter. We can see here the table of MUX 5 to 0, and we can see all the combinations down on this table. The single channel conversions are shown here, ADC 0 to ADC 7 and ADC 8 to ADC 15. And then we had the differential inputs showing here and down here, and some with gains of 10, 200, and others with no gain at all. Looking at how we can program the ADC, we can firstly set the ADC up. We turn on the power. We choose whether we're doing single conversion or free running. If you're using interrupts, then enable the local interrupts. we need to select the conversion speed, select the reference voltage, choose whether doing left aligned 8-bit or right aligned 10-bit, and set the multiplexer to the correct channel. Now, if you're only ever reading one channel, set up the ADC as described, have it in free running mode, and now you can just read the ADCH and ADCL registers, and they will hold the value from the last conversion. If you are looking at multiple channels, you need to actually write a function to read the ADC channel. The function will select the correct ADC channel, start the conversion, wait for the conversion to be complete, and then return the converted value. In this programming example, we will use single channel conversion using the free running mode. And we are going to do an 8-bit conversion of channel 1, ADC1, and output the result to port C. The structure diagram is shown here, set up ADC, set up ports, and then output ADC to port C. So looking at the code, we have the setup routine called here, the while one, and we just continuously read ADCH and store it in port C. Looking at the setup itself, we have DDRC, sets all of port C for output. Then we're going to look at the ADMUX register. So the ADMUX register is shown down here. The first 2 bits are the reference bits. If I go to the reference bits here, we want to be using the AVCC external pin, so that's set to 0, 1. We want to be left aligned, so that bit here should be A1. Then we'll look at the multiplexer. If I go down to here, we can see that ADC1, we need these figures to be all 0 apart from MUX 0. So we will come back to here and make the bit a 1. So looking at in our code, we can see that this bit here is going to be 0, 1. That bit's going to be a 1. These will all be zeros, apart from that bit there, and we can see that written in that statement. So looking at the ADCSRA register, this one will be a 1 to turn the power on. We're going to set this to slow mode, so 1, 1, 1. And we need to set this one here to be free running, auto select. So we can see that the result will be, we need to start the conversion as well. So we can see it'll be 1, 1, 1, 0, 0, 1, 1, 1. Now with the ADCSRB, if we look at that register, we can see that by default the system is running in free running mode. So I have placed this code into Microchip Studio. There is it down there, and I have downloaded it to the Mega Pro board. We can see that in action. There's a board there, there's pot we're using, and we can see as we turn the pot up full, the output is going up. Similarly, if we turn the pot down, the result is going down. So we are reading ADC1 and outputting it to port C. If you need to read 2 or more channels, then you need to use a function shown below. The function here is read ADC, and we have a parameter channel. Channel is then loaded into the ADMUX register. We start the conversion, we wait for the conversion to be complete, and then we return the value ADCH. So it's an 8-bit conversion, so the function is a char. Looking how it's called, we call the function, and this parameter here is the value that we want loaded into the ADMUX register. We can see an example of the char read ADC function here. So here's a function that we looked at before, and it's called in the main routine here. So what we want to do is read pot 1, pot 2, and output it to the display. If we look at here, there's the start conversion. That's bit 6. We set bit 6 to start the conversion, and then we check it to see when it's 0 and we know it's finished. And that's your start conversion and while conversion running. We have pot 1, which is loaded into the ADMUX register. We can see the ref is set to the external reference voltage. We are doing left adjust, and then we are either going to do ADC1 or ADC2. That's shown here. When we start the process, we set up and we actually initialize the display, but the main thing here is we enable the ADC and we set the slow speed, but we are not starting the ADC at this point. Then we come into here, we read the ADC, we pass the channel number to the function. It takes the conversion and returns that value, puts into pot 1. We put the channel number for pot 2 into the function, and it returns it there as well. I have written the code in Microchip Studio and downloaded it to the Mega Pro board. We can see it running. Pot 1 up here, we can see when we adjust it, it's going up and down, and pot 2 as well. So we can read 2 ADC signals using the read ADC function.